Our first topic for this module is functions. A function is a rule which takes a set of inputs and assigns to each an output. Before we can talk about the kinds of rules which produce functions, let's set up some notation. Let x and y be sets. When specifying a function named f, we write f goes from x to y. F takes its inputs from the set x and produces outputs in the set y. This notation here should be read as little x is in capital X. So x is a member of capital X. For a given input x, we write f of x for its output. Sometimes we write an arrow from a single input to its output. But don't confuse this notation, which is for a single element, with the notation above, which tells you all the inputs and outputs of a function. We have special names for the set of inputs and the set of outputs of a function. The set of inputs of f is called its domain. The set of outputs is called its range. So when we write f goes from x to y, we are saying that x is the domain of f and y is its range. Now let's talk about what kinds of rules are allowed when making a function. A rule can take the form of a formula, or a table, or a graph, or even a process for computing the output. The only condition is that for each value in the domain, there must be one single output from the range which it is sent to. A function is not allowed to be undefined on any of its inputs, and we'll say more about this in the coming problems. Let's move on to our first problem. Here we specify x to be the set containing 1, 2, and 3, and y to be the set of 1 through 6. We define a function f which takes capital X as its input, that's its domain, and y is its possible outputs, that's its range. The rule for f is that it doubles its inputs. Let's fill in a table of f and write its formula. If we take 1 as the input for f, then f outputs 2 times 1, f outputs 2. We write f of 1 equals 2. This can also be read as the output of 1 is 2. If instead we take 2 as the input of f, then its output is twice 2, or 4. So we write f of 2 equals 4. Finally, if the input to f is 3, the output is 6. We're done writing the table for f since we've covered all of its inputs. We specified the output for each value in f's domain. You'll notice that there are a number of outputs which didn't appear. We didn't see 1, 3, or 5 as the output of f. It's okay if some members of the range do not get mapped to. The range of a function is allowed to be larger than the actual set of outputs. In order to have a valid function, we only need to ensure that it is defined for all of the inputs in its domain. Here we can now write a general formula for f. F of input x is 2 times x. Here again, x is the input of f, and f of x is our notation for its output. In calculus, most of the functions we work with take real numbers as inputs and have real numbers as their outputs. So we've written R, the set of real numbers, for both the domain and for the range of f. Let's look at a simple example. If f of x is the function x squared minus 1, then f takes a real number as its input, it squares it, subtracts 1, and gives that as its output. So f of 1 equals 1 squared minus 1, or 0. And f of 2 equals 2 squared minus 1, which is 4 minus 1, or 3. We can plot these on a graph of f to get the points 1, 0, and 2, 3. If we compute some more points, we can fill in the graph for this parabola. This function can take any real number as its input, but it won't give us its output anything smaller than minus 1. We can still say that f takes real numbers and produces real numbers. However, there are some functions that are not defined for all real inputs, meaning that for some values of x, they won't produce an output. These bad inputs are not in the domain of the function. In problem 2, we're asked to determine the domain of the square root function. We'd like to know where this function is defined. Let's evaluate the square root function at some simple values. The square root of 0 is 0, so f of 0 is 0. The square root of 1 is 1, so f of 1 is 1. Also, the square root of 4 is 2, since 2 times 2 equals 4. So f of 4 is 2. We can plot these points, 0, 0, 1, 1, 4, 2, all on our graph of f. Any positive real number has a square root, as you can see by filling in this graph. The square root of 3 is found by looking at the height of this graph, above x equals 3. You can see that the square root of 3 is somewhere between 1 and 2. Now let's talk about the square root of negative numbers. If you multiply a real number against itself, you always get a positive number back. A positive times a positive is a positive. A negative times a negative also gives a positive number. So there's no real square root of a negative number. Thus, f is undefined for negative numbers. The domain of f is all real numbers that are 0 and larger. We call these non-negative real numbers. Let's write that f is a function from the non-negative reals to all of r. Here's our next problem. We're asked to find the domain of the function 1 over x. This formula, f of x equals 1 over x, tells us what f outputs for each of its inputs. For instance, if we let x be the input 2, then f of 2 is 1 over 2, or simply 1/2. We can plot this pair of input and output on a graph as the point 2, 1/2. Let's compute a few more points on the graph of f. For input 1, f produces 1 over 1, or just 1. If we consider f equals 1/2 as an input, then f of 1/2 is 1 over 1/2, which equals 2. Let's plot these points. We can also evaluate f at negative values. F of -1 is 1 over -1, or simply -1. F of -2 is 1 over -2, or -1/2. F is also defined between these values, so once we plot them, we fill in the curve to see all the other outputs of f. There's one real value for x which won't produce an output by the rule given for f. If x equals 0, then f of x ought to be 1 over 0, but this is not a number, so f is undefined at x equals 0. This means the domain of f is all real numbers excluding 0. We write that f goes from r minus 0 to r. Here r minus 0 is the set of all real numbers with x not equal to 0. You'll notice that 0 is not an output of f, since the graph never touches the x-axis. We could have written that the range of f was also r minus 0. But we don't have to do it this way. As long as the range contains all the outputs, and possibly more, then we're okay. Our last problem on this topic asks us to find the domain of this rational function. A rational function is simply a polynomial divided by another polynomial. Here we have 1 on top, and x squared plus 3x plus 2 in the denominator. We can find the domain of f without drawing a picture. Fractions aren't defined when their denominators are 0. So f is undefined when x squared plus 3x plus 2 is equal to 0. If we factor x squared plus 3x plus 2, we get x plus 2 times x plus 1. You can check that the coefficient of the linear term 3 is equal to 2 plus 1, and the constant term of our original polynomial, which is 2, is 2 times 1. So the roots of the denominator are x equals minus 2 and x equals minus 1. These values are the values that make the denominator 0, and hence make f undefined. The domain of f is R, removing the points minus 1 and minus 2. Here this set is the set of all real numbers except minus 1 and minus 2. We write f as a function going from this set and producing all real numbers. We are ready to move on, but we will come back to this topic once we've introduced more functions.